Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scale with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys. regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbits would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into 2 or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievskii-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. Why space is nearly empty? When you look up at the night sky, space appears crowded with stars, planets, and galaxies. Photographs from telescopes show spectacular images of colourful nebulae, dense star clusters, and brilliant galaxies packed with hundreds of billions of stars. These images create an impression of a cosmos teeming with matter, a universe filled to the brim with celestial objects. But this impression is profoundly misleading. Space is almost unimaginably empty. The distances between objects are so vast and the objects themselves so small relative to those distances that if you could somehow travel to a random location in the universe, the overwhelming likelihood is that you would find yourself surrounded by nothing. No stars, no planets, no gas, no dust, for distances stretching farther than you could travel in a lifetime, even at the speed of light. To understand just how empty space is, consider the space between Earth and the Moon. The Moon orbits at an average distance of about 380,000 kilometers from Earth. That's far enough that you could fit all the other planets in the solar system side by side in the gap between Earth and the Moon, with room to spare. Now imagine taking a sphere with a radius equal to this Earth-Moon distance. Within that enormous volume, there are only two objects of any significant size, Earth and the Moon themselves. Everything else is emptiness, with only occasional atoms of gas or tiny dust particles scattered throughout. The situation becomes even more extreme when you consider the space between planets. Earth orbits about 150 million kilometers from the Sun. Mars orbits about 230 million kilometers from the Sun. The distance between Earth and Mars varies as both planets orbit, but at their closest approach, they're separated by about 55 million kilometers. This vast gulf contains essentially nothing. No planets, no moons, just a scattering of asteroids so small and so far apart that even if you were traveling through this region, you would be extraordinarily unlikely to come anywhere near one. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spaceships must carefully navigate, is in reality astonishingly sparse. The belt contains hundreds of thousands of asteroids larger than 1 kilometer across and millions of smaller ones. This sounds like a lot, and by the standards of everyday experience it is. But these asteroids are spread across an enormous volume of space, a region extending from about 300 million kilometers to 500 million kilometers from the Sun, and spanning the full circumference around the Sun at these distances. The result is that the average distance between asteroids is measured in millions of kilometers. If you were to travel through the asteroid belt, you would see nothing for days or weeks of travel before coming near even a single asteroid. The density of matter in the asteroid belt averages far less than 1 particle per cubic kilometer. Compare this to air at sea level on Earth, which contains about 10 to the 25th particles per cubic kilometer, a 1 followed by 25 zeros. The asteroid belt, despite containing countless asteroids, is millions of billions of times less dense than the air you're breathing right now. Every spacecraft we've sent through the asteroid belt, and many have made the journey, has passed through without incident, without needing to dodge asteroids, simply because the belt is so incredibly empty. Beyond the planets, the emptiness becomes even more profound. The nearest star to our Sun, Proxima Centauri, lies about 40 trillion kilometers away, a distance so vast that light, traveling at 300,000 kilometers per second, takes over 4 years to cross it. If you scaled the Sun down to the size of a basketball, Earth would be a grain of sand orbiting about 25 meters away, and Proxima Centauri would be another basketball more than 6,000 kilometers away. The sphere of space between these two basketballs contains essentially nothing. No planets, no asteroids, no comets that we know of, just occasional atoms of hydrogen, some dust particles so rare you could travel for years without encountering one, and the faint pressure of starlight. This interstellar space contains gas, but calling it gas seems almost misleading given its extreme tenuousness. In the space between stars, the density averages about 1 atom per cubic centimeter. For comparison, air at sea level contains about 10 to the 19th atoms per cubic centimeter. Interstellar space is less dense than air by a factor of 10 million trillion. The best vacuum we can create in laboratories on Earth, in the most sophisticated vacuum chambers, is still millions of times denser than the average density of interstellar space. Even the densest regions of interstellar space, the molecular clouds where stars form, are extraordinarily sparse by terrestrial standards. These clouds, which appear dark and opaque in photographs because they block light from stars behind them, contain perhaps 1 million atoms per cubic centimetre at their densest cores. This is dense for space, but it's still 10 trillion times less dense than air on Earth. You could travel through the densest part of a molecular cloud and not even notice. There would be no resistance to your motion, no sense of passing through anything. The emptiness extends to larger scales as well. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with vast quantities of gas, dust, and dark matter. Yet these hundreds of billions of stars occupy a disk about 100,000 light-years across and roughly 1,000 light-years thick at the Sun's location. The stars are so far apart that if you were to travel to a random location within the galaxy, you would find yourself in interstellar space, far from any star. The average distance between stars is about 5 light-years. At the scale where stars are separated by light-years, the stars themselves, objects typically about 1 million kilometers across, are essentially point-like. They occupy a negligible fraction of the galaxy's volume. Between galaxies, the emptiness reaches its most extreme. The space separating galaxies is called intergalactic space, and it's even emptier than interstellar space. The density of matter in intergalactic voids, the enormous empty regions between galaxy clusters, is approximately 1 atom per 10 cubic meters. Think about that. You could take a cube of space 10 meters on each side, large enough to contain a small house, and on average, it would contain just 1 single atom. This is as close to perfect vacuum as nature achieves anywhere in the universe. The scale of intergalactic distances staggers comprehension. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, lies about 2.5 million light-years away. The space between our galaxy and Andromeda is largely empty, except for a few dozen small dwarf galaxies and some scattered gas clouds. Beyond our local group of galaxies, the distances grow even more immense. The Virgo cluster of galaxies, which contains thousands of galaxies, lies about 50 million light-years away. The space between galaxy clusters is measured in tens of millions to hundreds of millions of light-years, and it contains essentially nothing. So why is space so empty? The answer lies in how the universe evolved after the Big Bang. In the earliest moments, the universe was actually extremely dense. All matter and energy were compressed into a tiny volume. But the universe has been expanding ever since, and as it expands, the matter within it spreads out, becoming less and less dense. The expansion of space itself increases the distances between objects, diluting the average density of matter throughout the cosmos. Gravity works against this dilution by pulling matter together into clumps. Regions that were slightly denser than average in the early universe attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to the denser regions and became emptier. Over billions of years, this process created the structure we see today. Matter concentrated into stars, which are concentrated into galaxies, which are concentrated into galaxy clusters and superclusters with vast voids between them. But even with gravity concentrating matter into structures, the vast majority of space remains empty because the fundamental ratio of matter to space is so low. If you took all the matter in the observable universe, every atom in every star, planet, gas cloud and galaxy, and spread it uniformly throughout all of space, the density would be about 5 atoms per cubic meter. This is the average density of the universe, and it reveals that matter is extremely rare. The universe is about 5 atoms of matter per cubic meter on average, with the rest being empty space and dark energy. The emptiness of space has profound implications. It means that collisions between stars are extraordinarily rare, even in the centers of galaxies, where stars are most densely packed. When 2 galaxies collide, and galaxy collisions are fairly common on cosmic timescales, the stars themselves almost never hit each other. The galaxies pass through each other, like two clouds of gnats interpenetrating, without individual gnats colliding, because the distances between stars are so large compared to the stars' sizes. The emptiness also means that space travel is, in some ways, easier than it might otherwise be. A spacecraft travelling through space doesn't need to constantly dodge debris or navigate through fields of material. Space is clear. The challenges of space travel come not from crowding but from the vast distances between destinations and the energy required to cross those distances. Light from distant objects travels through this emptiness for billions of years, crossing intergalactic voids, interstellar space, and the relative crowding of planetary systems to eventually reach our telescopes. The fact that we can see distant galaxies at all, objects billions of light years away, testifies to how empty space is. If space were filled with gas or dust at densities even remotely approaching terrestrial conditions, the light would be scattered and absorbed long before travelling such distances. The emptiness of space is not a coincidence or an accident. It's a fundamental consequence of the universe's expansion, the initial density of matter after the Big Bang, and the way gravity organises that matter into structures. The spectacular images of galaxies, nebulae, and star clusters show us the rare locations where matter has concentrated. But these are the exceptions, the islands of matter in an ocean of emptiness. The typical state of the universe is not the crowded star field or the dense nebula. It's the dark, cold, nearly perfect vacuum of intergalactic space, where a single atom might drift alone for years before encountering another, where the nearest star is so distant that its light takes millions of years to arrive, and where the overwhelming reality is not presence but absence, not matter but void, not something but nothing, extending in all directions for distances that dwarf the span of human comprehension. Why silicon-based life forms might be possible. For as long as scientists have contemplated life beyond Earth, one element has persistently captured imaginations as a possible alternative to carbon: silicon. Science fiction has explored silicon-based aliens in countless stories, from rock-like creatures that metabolize minerals to crystalline beings that think at geological timescales. But these fictions rest on a foundation of genuine chemistry. Silicon sits directly below carbon in the periodic table, shares many of carbon's most important properties, and is far more abundant in Earth's crust than carbon. Yet despite this abundance and chemical similarity, silicon never became the basis for life on Earth. Understanding why silicon-based life might still be possible elsewhere requires examining both the remarkable parallels between silicon and carbon chemistry and the significant obstacles that would need to be overcome. Carbon's dominance in biochemistry stems from several key properties. Carbon atoms can form 4 strong covalent bonds with other atoms, allowing them to link together into chains, branches, and rings of almost unlimited complexity. A single carbon atom might bond to 4 other carbon atoms, creating a 3-dimensional network. Or carbon atoms might link into chains hundreds or thousands of atoms long, with various other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, attached at different positions. This versatility allows carbon to form millions of different molecules, from simple methane with 1 carbon atom to DNA molecules containing billions of carbon atoms arranged in precise sequences that store genetic information. Silicon shares carbon's ability to form 4 covalent bonds. The electron configuration that gives carbon its bonding properties is mirrored in silicon, making silicon capable of forming similar structures: silicon chains, silicon rings, silicon networks. In fact, silicon chemistry forms the basis of an entire class of synthetic materials called silicones, which consist of chains of alternating silicon and oxygen atoms with organic groups attached. These materials, familiar as sealants, lubricants, and medical implants, demonstrate that silicon can indeed form large complex molecules. But silicones are human inventions, created in laboratories and factories. Nature has not produced silicon-based organisms, at least not on Earth, despite silicon being about 900 times more abundant in Earth's crust than carbon. The primary obstacle to silicon-based life under Earth-like conditions is silicon's relationship with oxygen. When carbon reacts with oxygen, when it burns, it forms carbon dioxide, a gas at normal Earth temperatures. This gas can be easily expelled from an organism and recycled back into the environment. Plants take in carbon dioxide and use it to build sugars through photosynthesis. Animals exhale carbon dioxide as a waste product of metabolism. Carbon dioxide dissolves readily in water, allowing it to be transported in blood and participate in various chemical reactions. The carbon cycle that sustains Earth's biosphere depends on carbon dioxide being gaseous, mobile, and chemically accessible. Silicon's equivalent compound is silicon dioxide, silica, quartz, sand, rock. When silicon burns with oxygen, it forms a solid. This solid is extremely stable, nearly insoluble in water, and chemically unreactive under normal conditions. An organism that metabolizes silicon and oxygen the way Earth organisms metabolize carbon and oxygen would accumulate solid mineral waste inside its body or would need to excrete sand. The waste products of silicon metabolism cannot easily be transported in fluids, cannot be exhaled as gas, and cannot be recycled through environmental cycles the way carbon dioxide can. This fundamental difference makes silicon-oxygen chemistry poorly suited for biochemistry on worlds with oxygen-rich atmospheres and liquid water. However, removing oxygen from the equation changes the possibilities dramatically. In environments where oxygen is absent or rare, silicon chemistry behaves very differently. Silicon forms stable bonds with hydrogen, creating silanes, molecules analogous to hydrocarbons, but with silicon replacing carbon. The simplest silane is silane itself, with one silicon atom bonded to 4 hydrogen atoms, analogous to methane. Longer chains are possible, disilane with 2 silicon atoms, trisilane with 3, and so on. These silicon-hydrogen chains are reactive and unstable compared to carbon-hydrogen chains. But in the absence of oxygen, they might persist long enough to serve biological functions. Temperature plays a crucial role in silicon chemistry. At Earth's surface temperatures, silicon-silicon bonds are relatively weak compared to carbon-carbon bonds. Silicon compounds tend to break apart more easily, making long, stable silicon chains difficult to maintain. But at much colder temperatures, the kinds found in the outer solar system, silicon chemistry becomes more favorable. Chemical reaction rates slow down dramatically at low temperatures, which could actually help stabilize silicon compounds that would rapidly decompose at room temperature. Meanwhile, some of the alternative solvents that might replace water at these temperatures could interact with silicon compounds in ways that favor complex chemistry. Liquid methane and ethane, which exist naturally on Saturn's moon Titan at temperatures around -180 degrees Celsius, represent one possibility. In these hydrocarbon seas, water is as hard as rock and oxygen is locked away in ice and minerals. Silicon compounds might dissolve in liquid hydrocarbons more readily than in water, and without oxygen to react with, silicon could potentially form the complex, diverse molecules that life requires. The chemistry would be radically different from Earth's biochemistry. Reaction rates would be thousands of times slower, molecules would have different shapes and properties, and the fundamental mechanisms of energy storage and information transfer would need to be reimagined. But the basic requirements for life, complex molecules that can store information, catalyze reactions, and self-replicate, might still be achievable with silicon as the central element. Liquid nitrogen, which exists at even colder temperatures, offers another potential solvent. Nitrogen becomes liquid at -196 degrees Celsius at Earth atmospheric pressure. A world with lakes or oceans of liquid nitrogen would be incomprehensibly cold by Earth standards, but chemical reactions would still occur, just very slowly. Silicon compounds might be more stable and diverse at these extreme temperatures, allowing them to form the kinds of complex structures that life needs. Another approach to silicon-based life involves thinking beyond complete replacement of carbon. Instead of imagining organisms built entirely from silicon, consider hybrid biochemistries that use both elements. Silicon might form structural components, while carbon handles information storage and catalysis. Silicon-oxygen minerals could serve as skeletal elements, providing rigid support structures that carbon-based soft tissues attach to. This is essentially what Earth organisms do. Bones, shells, and the glass-like structures of diatoms all incorporate silicon compounds, though the fundamental biochemistry remains carbon-based. A true silicon-based organism would integrate silicon more deeply into its biochemistry, perhaps using silicon-containing molecules for energy storage, membrane structure, or even genetic material. The information storage challenge represents one of the most significant hurdles for silicon-based life. DNA and RNA work remarkably well as information storage molecules because they're stable enough to preserve information over time, but flexible enough to be copied and modified. The sugar phosphate backbone provides structural support, while the nitrogen bases store actual information through their sequence. Could silicon replace the carbon in the sugar molecules? Silicon-containing analogues of sugars and nucleotides have been synthesized in laboratories, demonstrating that such molecules can exist. Whether they could reliably store and transmit information across generations in a living organism remains unknown, but the chemistry doesn't appear to forbid it outright. Energy metabolism in silicon-based organisms presents another puzzle. Earth organisms primarily extract energy by rearranging chemical bonds, breaking bonds in food molecules, and forming new bonds in waste products, capturing the released energy in the chemical bonds of ATP. Silicon-based organisms would need analogous processes. Perhaps they could oxidize silanese to release energy, though the solid silicon dioxide waste product would be problematic. Or they might use entirely different metabolic pathways based on silicon's interaction with halogens like fluorine or chlorine, creating different waste products that could be more easily managed. In extremely cold environments, metabolic rates could be extraordinarily slow. A silicon-based organism might take years to grow or reproduce, operating on timescales that would make watching grass grow seem rapid by comparison. The evolution of silicon-based life would require a planet with very specific conditions. Silicon would need to be available in reactive forms rather than locked into stable minerals. The temperature would probably need to be very cold to favor silicon chemistry over its tendency to decompose. Oxygen would need to be absent or rare to prevent silicon from forming insoluble silicon dioxide. A suitable solvent other than water would need to exist: liquid hydrocarbons, liquid ammonia, or something even more exotic. These conditions might exist on certain moons in the outer solar system, on rogue planets drifting through interstellar space, or on exoplanets orbiting dim red dwarf stars where temperatures never rise above the freezing point of water. Titan, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its extremely cold temperatures, represents perhaps the best candidate in our solar system for silicon-based life. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will explore Titan's surface and could potentially detect signs of exotic biochemistry if it exists. The mission won't specifically look for silicon-based life. Nobody knows exactly what signatures such life would produce, but it will analyze organic chemistry in Titan's lakes and atmosphere, searching for patterns that might indicate biological processes. Even if silicon-based life exists nowhere in the universe, Studying the possibility expands our understanding of chemistry's relationship to biology. It forces us to question our assumptions about what life requires and what forms it might take. Every element brings different properties, different strengths and weaknesses, different possibilities and constraints. Carbon happened to be the element that worked on Earth under Earth's conditions, but Earth represents just one set of conditions among countless possibilities across the universe. The theoretical possibility of silicon-based life also highlights a challenge in searching for extraterrestrial life. Most of our detection methods assume life will be similar to Earth's, producing oxygen, methane, or other gases we associate with biological activity, building structures we would recognize using chemistry we understand. But silicon-based life operating in liquid methane seas at minus 180 degrees Celsius would produce completely different signatures. It might metabolize compounds we consider inert waste products and excrete substances we consider essential for life. Its waste products might be our nutrients, and vice versa. We might look directly at a world covered in silicon-based organisms and not recognize it as inhabited because we're searching for carbon signatures. Silicon-based life might be possible in environments so different from Earth that the very definition of life becomes strained. Perhaps silicon-based entities would be better described as self-organizing chemical systems rather than organisms in any sense we would recognize. They might grow and reproduce on timescales of centuries. Their metabolism so slow that a single thought, if they think at all, might take years to form. They might not have discrete bodies with clear boundaries between self and environment, but instead exist as diffuse networks of silicon-based chemistry spread across vast areas. They might not die in any meaningful sense, but simply cease maintaining organization and gradually disperse back into their environment. Why silicon-based life forms might be possible comes down to chemistry being flexible, creative, and opportunistic. The laws of chemistry operate everywhere in the universe, but they produce different outcomes under different conditions. Silicon's chemical properties give it potential as a basis for complex, self-organizing systems under the right circumstances. Circumstances that apparently don't exist on Earth, but might exist elsewhere. From the hydrocarbon lakes of Titan to hypothetical ice worlds, orbiting dim stars to environments we haven't yet imagined, silicon might be constructing molecules, storing information, and powering metabolisms in ways that parallel carbon-based life, just enough to recognize as living while remaining alien enough to challenge everything we thought we knew about biology, proving that life's possibilities extend beyond the single example we know to encompass chemistries as diverse as the cosmos itself. Why gas giants spin at different speeds? The giant planets of our solar system rotate at speeds that seem almost impossible when you first encounter the numbers. Jupiter, the largest planet, completes a full rotation in just under 10 hours. Imagine standing on a world where a single day passes more than twice as fast as the time it takes to watch a long movie. Saturn spins even faster in some ways, though its rotation is more complex. Uranus and Neptune, the ice giants farther out, rotate at their own distinct rates, each with rotational periods that tell a story about how they formed and what has happened to them over billions of years. Picture Jupiter in your mind, a massive sphere of swirling clouds in shades of cream, brown, orange, and red. This giant world contains more mass than all the other planets combined, yet it spins so rapidly that it bulges noticeably at its equator. If you could somehow stand at Jupiter's equator, you would be moving at over 28,000 miles per hour, far faster than anything on Earth except spacecraft. The planet's day, the time it takes to complete one rotation, is only about 9 hours and 55 minutes. This incredible speed creates winds that race around the planet in alternating bands, some flowing eastward, others westward, creating the distinctive striped appearance we see in telescopes. But here's where it becomes fascinating. Not all of Jupiter spins at the same rate. The planet is made primarily of hydrogen and helium in gaseous and liquid forms, with no solid surface to anchor to. The equatorial regions spin slightly faster than the polar regions, completing a rotation in about 5 minutes less time. This differential rotation is possible because Jupiter isn't a rigid body like Earth. Different latitudes can rotate at different speeds, sliding past each other in the fluid interior. The deep interior, where hydrogen is compressed into a metallic liquid state, may rotate at yet another rate, one that scientists are still working to measure precisely. Saturn presents an even more puzzling picture. This ringed giant is less dense than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, with a day lasting only about 10 hours and 33 minutes, causes an even more pronounced equatorial bulge than Jupiter's. The planet's diameter at the equator is nearly 10% larger than its diameter from pole to pole. Picture a sphere that's been squeezed from the top and bottom while being stretched around its middle, all due to the centrifugal force of its rapid spin. What makes Saturn particularly mysterious is that determining its exact rotation rate has proven remarkably difficult. Unlike rocky planets, which have surface features that can be tracked, or planets with strong magnetic fields that rotate with the deep interior, Saturn presents challenges. Its magnetic field is almost perfectly aligned with its rotation axis, which makes it hard to use as a reference. Different methods of measuring Saturn's rotation have given different results, sometimes varying by as much as several minutes. The planet's atmosphere rotates at different speeds at different latitudes, just like Jupiter's. But figuring out the rotation rate of Saturn's deep interior, the true rotation rate of the planet, remains one of the ongoing puzzles in planetary science. The rings of Saturn add another layer to this story. These rings are made of countless particles of ice and rock, each one orbiting Saturn independently, according to the laws of orbital mechanics. The inner parts of the rings orbit faster than the outer parts, completely independent of how fast the planet itself spins. If you could watch from above Saturn's North Pole, you would see the rings spinning like a vast flat disk, while beneath them the planet rotates at its own separate rate. And within the planet, different layers rotate at their own speeds as well. Now travel farther out to Uranus, the tilted giant. This planet rolls through space like a ball rolling along the ground, with its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Something in Uranus's past, likely a massive collision with another planet-sized object, knocked it onto its side. Despite this dramatic tilt, Uranus rotates relatively quickly, completing one rotation in about 17 hours and 14 minutes. This is slower than Jupiter and Saturn, but still far faster than Earth's 24-hour day. The interior structure of Uranus affects its rotation in ways different from the gas giants. Uranus is classified as an ice giant rather than a gas giant because, beneath its hydrogen and helium atmosphere, it contains a much larger proportion of water, methane, and ammonia ices. These materials, compressed under tremendous pressure, create a layered interior that may not mix as freely as the interiors of Jupiter and Saturn. This layering could mean that different depths within Uranus rotate at substantially different rates, though our knowledge of the planet's interior remains limited from Earth. Neptune, the farthest giant planet, spins with a period of about 16 hours and 6 minutes, slightly faster than Uranus, despite being similar in size and composition. Neptune's deep blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Like the other giant planets, Neptune shows differential rotation, with its equatorial atmosphere moving at a different speed than the atmosphere at higher latitudes. The planet has the strongest winds in the solar system, with some storms showing wind speeds exceeding 1,200 miles per hour. These winds don't simply follow the rotation of the planet. They race around at speeds that are faster than the underlying rotation rate, driven by heat flowing from Neptune's interior. The question of why these giants spin at such different speeds takes us back to the formation of the solar system. Imagine the early solar system as a vast rotating disk of gas and dust surrounding the young sun. Within this disk, material began to clump together, forming the seeds of planets. As these clumps grew larger through gravity, pulling in more material, they began to spin faster due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms in. Each growing planet accumulated material that was already moving in orbit around the Sun. This material had angular momentum, and as it fell onto the growing planet, it transferred that momentum to the planet itself. The amount of spin the planet ended up with depended on exactly how this accretion process occurred, the trajectories of the infalling material, the timing of impacts, and whether the material came in symmetrically or from preferred directions. Jupiter and Saturn, being closer to the Sun and in regions with more available material, grew faster and larger than Uranus and Neptune. Their rapid growth meant they could capture enormous amounts of gas from the protoplanetary disk before it dissipated. This gas fell onto the planets from all directions, and the net effect was to spin the planets up to high rotation rates. The exact speed depended on the complex details of how the gas flowed onto the growing planet and how the planet's gravity interacted with the surrounding disk. The spin rates were also affected by large impacts during the final stages of planet formation. When planet-sized objects collided, they didn't just add their masses together, they also exchanged angular momentum. The angle and speed of impact determined whether the collision would speed up the planet's rotation, slow it down, or even change its axis of rotation. Uranus's extreme tilt almost certainly resulted from one or more giant impacts that occurred late in its formation. Inside these spinning giants, the story continues. The rapid rotation creates strong Coriolis effects that organize the atmospheric flows into bands and zones. Rising warm gas gets deflected by the planet's rotation, creating the jet streams that race around the planets at different latitudes. In Jupiter's case, these jets are remarkably stable, maintaining the same patterns for centuries or longer. The rotation also affects the planet's magnetic fields, which are generated by the movement of electrically conducting fluids in their interiors, liquid metallic hydrogen in Jupiter and Saturn, and perhaps ionic water solutions in Uranus and Neptune. The differential rotation, the fact that different parts of these planets spin at different rates, creates zones of shearing where adjacent layers of fluid slide past each other. These shear zones can become unstable, spawning turbulence and storms. The Great Red Spot on Jupiter, a storm larger than Earth that has persisted for centuries, exists in a region where different wind speeds interact. The storm itself rotates, but at a rate different from the planet's overall rotation, caught in a complex interaction between different atmospheric layers. As these planets continue their journeys around the Sun, their rotation rates change, though extremely slowly. Gravitational interactions with their moons cause tidal effects that gradually transfer angular momentum between the planet and its satellites. This process is the same one that has locked our moon so that it always shows the same face to Earth, though it operates much more slowly on the giant planets due to their enormous masses. Jupiter's large moons are very gradually moving away from the planet, carrying angular momentum with them, which means Jupiter's rotation is slowing down, but this process operates over timescales of billions of years. The interiors of these planets remain largely mysterious, hidden beneath thousands of miles of atmosphere and fluid layers. Scientists use the planet's rotation rates, combined with precise measurements of their gravitational and magnetic fields, to deduce what must be happening in the unseen depths. The exact rotation rate of the deep interior tells us about the distribution of mass within the planet and how rigidly different layers are coupled together. Variations in the gravity field, measured by spacecraft flying past, reveal how mass is distributed between the equator and the poles, which in turn reveals how the rotation has shaped the planet's interior structure. Each of these giant worlds continues to spin through the darkness of space, their days flashing by in fractions of an Earth day, their atmospheres swirling in patterns that have persisted for eons. The differences in their spin rates encode the history of the solar system's formation, the random chance of ancient collisions, and the ongoing physical processes that govern how fluids behave under extreme conditions of pressure, temperature, and rotation. Understanding why gas giants spin at different speeds means understanding not just these four worlds, but the principles that govern planetary formation and evolution throughout the universe, wherever giant planets circle other stars. Where baby stars come from. Stars are not born in the bright, empty spaces between galaxies or in the clear voids of interstellar space. They emerge from darkness, from vast clouds of gas and dust that hang in the spiral arms of galaxies, regions so dense with obscuring material that they appear as black patches against the glowing background of the Milky Way. These stellar nurseries, called molecular clouds, are the cosmic wombs where stars begin their lives, places where gravity, temperature, pressure, and chemistry conspire to transform diffuse gas into brilliant spheres of nuclear fusion that will shine for millions or billions of years. The process begins with a molecular cloud, an enormous accumulation of gas and dust drifting through the galaxy. These clouds are cold, typically only 10 to 20 degrees above absolute zero, and they're composed primarily of molecular hydrogen, two hydrogen atoms bonded together, mixed with helium and trace amounts of heavier elements. The clouds also contain dust grains, tiny particles of silicates and carbon compounds, each grain smaller than a bacterium, but collectively making up about 1% of the cloud's mass. These dust grains play a crucial role despite their small mass contribution, shielding the interior of the cloud from starlight and cosmic rays, allowing it to remain cold enough for molecules to survive. Molecular clouds range in size from relatively small clouds, a few light years across, to giant molecular cloud complexes spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest star-forming regions at about 1,300 light-years from Earth, contains enough gas to make roughly 100,000 stars, like the Sun. The cloud extends across much of the constellation Orion, with the famous Orion Nebula marking just one small region where star formation is particularly active and visible. For stars to form, something must disturb these clouds, compressing them beyond a critical threshold where gravity overwhelms the internal pressure that normally keeps the cloud stable. This compression can come from several sources. A shockwave from a supernova explosion, travelling through space at thousands of kilometers per second, can slam into a molecular cloud and compress it. The spiral density waves that create the spiral arms of galaxies compress gas as it enters these regions, triggering star formation that lights up the spiral arms with young, bright stars. Even the radiation and stellar winds from existing massive stars can compress surrounding gas, triggering new generations of star formation in a process that propagates through the cloud. Once a region of the cloud is compressed, gravity takes control. The denser parts of the cloud pull in surrounding material, growing denser still. This runaway process would cause the entire cloud to collapse into one enormous star, but molecular clouds are turbulent places, filled with eddies and currents of gas flowing in different directions. This turbulence, combined with the cloud's rotation and magnetic fields threading through it, breaks the cloud into fragments. Each fragment, typically containing anywhere from a fraction of a solar mass to tens of solar masses, becomes the seed of a star or a small system of stars. As a fragment collapses, it heats up. This might seem counterintuitive. How does something heat up as it collapses in the cold of space? The answer lies in gravitational potential energy. As gas falls inward, it accelerates, gaining kinetic energy. When fast-moving atoms and molecules collide with other particles, they convert their kinetic energy into thermal energy, heat. The center of the collapsing fragment grows hotter and denser, while the outer regions continue to fall inward, feeding the growing concentration at the center. The collapse doesn't proceed smoothly or uniformly. The fragment rotates, inherited from the overall rotation of the molecular cloud, and conservation of angular momentum means it spins faster as it shrinks, just as an ice skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the center. Instead, material settles into a rotating disk around the growing protostar, the nascent star at the center. This disk, called a protoplanetary disk or protostellar disk, channels material toward the protostar, while the outer parts remain in orbit, eventually becoming the raw material from which planets might form. The young protostar, deeply embedded in the infalling gas and dust, is invisible at optical wavelengths. The surrounding cocoon of material absorbs any visible light the protostar emits and re-radiates it as infrared radiation. This is why infrared telescopes are essential for studying star formation. They can penetrate the dust and observe the protostars hidden within molecular clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed thousands of these embedded protostars, showing snapshots of stars at various stages of formation. As the protostar continues to accrete mass, its central temperature and pressure climb steadily. The journey from cold molecular gas to a hot protostar takes roughly 100,000 years for a Sun-like star, though this timescale varies depending on the protostar's mass. More massive protostars collapse more quickly because their stronger gravity accelerates the infall. Less massive protostars take longer, sometimes millions of years, to fully form. The protostar doesn't simply accrete all the material that falls towards it. Young protostars are violent, magnetically active objects. Magnetic field lines threading through the protostar, and its disk can become twisted and tangled by the rotation. And these magnetic fields launch jets, narrow beams of gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets are one of the most distinctive signs of active star formation. The Hubble Space Telescope has captured stunning images of these jets, often light years long, streaming away from young stars still hidden within their dusty cocoons. The jets serve an important function. They carry away angular momentum and energy that would otherwise prevent further accretion. Without some mechanism to remove angular momentum, the disk would simply spin faster and faster, and material would stop falling onto the protostar. The jets, along with stellar winds, outflows of gas from the protostar's surface, solve this problem, allowing the protostar to continue growing even as it spins. Where the jets slam into the surrounding molecular cloud, they create glowing knots and filaments called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them in the 1950s. These objects glow because the jet's high-speed collision with the ambient gas heats it to thousands of degrees, causing atoms to emit light. Herbig-Haro objects can move visibly over timescales of years, and they serve as signposts marking regions of active star formation. The accretion phase lasts for roughly 1 million years, though again this varies with stellar mass. During this time, the protostar is not yet a true star because no nuclear fusion occurs in its core. It shines from gravitational energy. The energy released as material falls onto its surface, and as it slowly contracts under its own weight. This contraction, described by Hermann von Helmholtz and Lord Kelvin in the 19th century, heats the interior gradually. Eventually, after millions of years of contraction and heating, the core temperature reaches approximately 10 million degrees Celsius. At this critical temperature, Protons moving at extremely high speeds collide with enough energy to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy. This ignition of hydrogen fusion marks the birth of a true star. The protostar becomes a main sequence star, entering a stable phase where the energy released by fusion creates outward pressure that balances gravity's inward pull. For a star like the Sun, this moment arrives roughly 10 million years after the initial collapse began. The newly formed star is now generating its own energy through nuclear reactions rather than relying on gravitational contraction. It will remain on the main sequence, fusing hydrogen in its core for about 10 billion years, 100 times longer than it took to form. Not all fragments in a molecular cloud form single stars. Many form binary or multiple star systems where two or more stars orbit each other. The fragmentation process can produce two separate cores within a single disk, each growing into a star. Or a protostellar disk can become gravitationally unstable and fragment, forming additional stars. About half of all stars exist in binary or multiple systems, making our single sun somewhat unusual. The smallest fragments don't have enough mass to ever ignite hydrogen fusion. Objects below, about 0.08 solar masses, roughly 80 times Jupiter's mass, never reach core temperatures high enough for hydrogen fusion. These failed stars, called brown dwarfs, glow dimly from their residual heat and from the fusion of deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than normal hydrogen. Brown dwarfs slowly cool over billions of years, gradually fading from view. The most massive fragments form massive stars, objects with tens of times the Sun's mass. These stars form quickly, sometimes in just a few 100,000 years, and burn brilliantly but briefly. They produce intense ultraviolet radiation that ionizes the surrounding gas, creating glowing H2 regions like the Orion Nebula. The radiation pressure from these massive stars is so strong that it can halt further star formation nearby, blowing away the remaining gas and effectively shutting down the stellar nursery. The wind and radiation from massive young stars create expanding bubbles in the molecular cloud, clearing out regions and compressing gas at the bubble's edges. This compression can trigger new star formation, creating generations of stars, with the oldest stars at the center and progressively younger stars toward the periphery. The entire process is self-propagating until the molecular cloud is either dispersed entirely or exhausted of dense gas. When the most massive stars explode as supernovae after just a few million years, they inject tremendous energy into their surroundings, heating and dispersing the remaining molecular cloud and enriching it with heavy elements created in the star and in the explosion. The shockwave from the supernova can compress nearby clouds, triggering new rounds of star formation. In this way, star formation is a cyclical process. Stars form from clouds, massive stars disrupt clouds, supernova shockwaves compress new clouds, and stars form again. The entire life cycle from molecular cloud to dispersed star cluster takes roughly 10 to 20 million years. The Orion Nebula, one of the most famous star-forming regions visible to the naked eye, contains stars that are only about 1 to 2 million years old, cosmic newborns still surrounded by the glowing remnants of the cloud that birthed them. Over the next few million years, the radiation from these young stars will disperse the remaining gas, leaving behind a star cluster that will gradually spread apart as its members drift through the galaxy. Understanding where baby stars come from means understanding one of the fundamental cycles of the cosmos. The gas from which stars form was once inside previous generations of stars. Those stars fused hydrogen into helium, helium into carbon and oxygen, and heavier elements still, then returned that enriched material to space through stellar winds and supernova explosions. That material mixed into molecular clouds and became incorporated into new stars, including our Sun, which formed about 4.6 billion years ago from a molecular cloud that contained the ashes of earlier stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that formed, lived, died, and seeded the molecular cloud from which the Sun and Earth eventually emerged, continuing the ancient cycle of stellar birth and death that has shaped the galaxy since stars first began forming over 13 billion years ago. What happens at the edge of a black hole? At the edge of a black hole lies one of the most extreme boundaries in the universe, a point of no return called the event horizon. This invisible surface marks the place where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape. Cross this threshold, and you are severed from the rest of the universe forever, drawn inexorably toward the singularity at the center. Understanding what happens at this edge requires thinking about space and time in ways that challenge everything. Our everyday experience tells us about how reality works. Imagine approaching a black hole from a safe distance. At first, it wouldn't look like much, just a region of absolute darkness against the star-filled background of space. But as you drew closer, you would begin to notice something strange happening to the light around you. Stars behind the black hole would appear distorted, their light bent around the black hole's mass in graceful arcs. Some stars would appear in multiple locations simultaneously as their light took different curved paths around the black hole to reach your eyes. This gravitational lensing creates a visual effect, like looking through a cosmic funhouse mirror, with the entire background of space warped and twisted around the dark sphere. The event horizon itself is defined by a specific radius from the center of the black hole, called the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For a supermassive black hole, like the one at the center of our galaxy, which contains about 4 million times the Sun's mass, the event horizon stretches millions of kilometers across. The radius grows linearly, with mass double the mass and you double the radius. Despite these varying sizes, the fundamental nature of the event horizon remains the same. It's the mathematical surface where the escape velocity equals the speed of light. Think about what escape velocity means. On Earth, you need to throw something upward at about 25,000 miles per hour for it to escape the planet's gravity and never fall back down. Get closer to a massive object and the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches 186,282 miles per second. The speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. But here's where things become truly strange. Time itself behaves differently near a black hole's edge. According to Einstein's general relativity, gravity doesn't just bend space, it warps time as well. The stronger the gravity, the slower time passes relative to an observer far away from the gravitational source. Near the event horizon, this time dilation becomes extreme. Picture two observers, one hovering safely far from the black hole, another descending toward the event horizon. The descending observer checks their watch, and everything seems normal to them. Time passes at its usual rate from their perspective. They breathe normally, their heart beats regularly, they think their thoughts at the normal pace. But to the distant observer watching through a powerful telescope, something bizarre is happening. The descending person appears to be moving slower and slower. Their movements become sluggish, their signals take longer and longer to arrive, and as they approach the event horizon, they appear to nearly freeze in place. This isn't an optical illusion or a trick of perception. Time genuinely runs slower in stronger gravitational fields. As the descending observer approaches the event horizon, each second they experience corresponds to longer and longer periods for the distant observer. At the exact moment they cross the event horizon, from the distant observer's perspective, Time for them appears to stop completely. They would appear frozen at the edge, never quite crossing over, their image becoming increasingly redshifted and dim, eventually fading from view entirely. But from the perspective of the person crossing the event horizon, nothing special happens at that precise moment. There's no wall, no barrier, no sensation of crossing a threshold. They would pass through the event horizon and continue falling inward, still experiencing time normally from their own reference frame. This is one of the most counterintuitive aspects of black holes. The event horizon is only special to outside observers. To someone crossing it, the moment passes without any local indication that anything significant has occurred. However, there is something that would become increasingly noticeable as you approached and crossed the event horizon: tidal forces. These arise because gravity weakens with distance, and different parts of your body would be at different distances from the black hole's center. If you fell feet first toward the black hole, your feet would experience stronger gravity than your head. This difference in gravitational pull creates a stretching force. For a stellar mass black hole, these tidal forces become extreme well before you reach the event horizon. The difference in gravitational pull between your head and feet would stretch you vertically while simultaneously squeezing you horizontally, a process astrophysicists have termed spaghettification. Long before reaching the event horizon, the tidal forces would overcome the molecular bonds holding your body together, stretching you into a thin stream of atoms. This would be an absolutely fatal experience occurring far from the event horizon itself. For supermassive black holes, the situation is different. Because they're so much larger, the tidal forces at the event horizon are actually quite mild. You could cross the event horizon of a supermassive black hole, and for a while at least, experience no unusual forces at all. The spaghettification would come later, as you continued falling inward toward the singularity where tidal forces eventually become infinite, regardless of the black hole's size. The event horizon is also where the nature of space and time exchange roles, in a sense. Outside the event horizon, you can choose your direction in space. You can go left or right, up or down, toward or away from the black hole. Time, on the other hand, only flows in one direction, forward. But once you cross the event horizon, this changes. Moving inward toward the singularity becomes as inevitable as moving forward in time is outside the black hole. Just as you can't choose to move backward in time in normal space, you can't choose to move away from the singularity once inside the event horizon. All possible paths through space-time, every trajectory you could take, lead inward. Light behaves strangely at the event horizon as well. Just outside the horizon exists a region called the photon sphere, where light can orbit the black hole in unstable circular paths. Photons at exactly this radius, moving in exactly the right direction, will circle the black hole indefinitely, though any tiny perturbation will cause them to either spiral inward or escape outward. If you could somehow position yourself at the photon sphere and look sideways, you might theoretically see the back of your own head as light from you travelled around the black hole and returned. At the event horizon itself, photons can move along the surface, neither escaping nor falling inward, but this is an unstable equilibrium. Any photon aimed even slightly inward will fall toward the singularity. Any photon aimed even fractionally outward will escape to infinity, though heavily redshifted by the time it reaches distant observers. The effects of gravitational redshift become extreme near the event horizon. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths, toward the red end of the spectrum and beyond into infrared and radio waves. A flashlight shining from near the event horizon would appear dimmer and redder to a distant observer. Right at the event horizon, light is redshifted infinitely, meaning the energy of any photon trying to escape becomes zero. This is another way of understanding why nothing can escape. Even light, trying to leave the event horizon, has all its energy drained away by the gravitational field, Black holes can rotate, and rotation adds another layer of complexity to the event horizon. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, space itself is being pulled around in the direction of rotation. There's a region called the ergosphere outside the event horizon, where this frame dragging is so strong that nothing can remain stationary. Everything must rotate with the black hole, even if it has enough energy to eventually escape. For a rotating black hole, the event horizon is actually smaller than it would be for a non-rotating black hole of the same mass, and it's oblate rather than perfectly spherical, bulging slightly at the equator. At the poles, you could get closer to the singularity before crossing the point of no return than you could at the equator. The material falling into a black hole doesn't simply disappear the moment it crosses the event horizon. Before crossing, matter often forms an accretion disk, a swirling disk of gas, dust, and plasma spiraling inward. Friction in this disk heats the material to tremendous temperatures, often millions of degrees, causing it to radiate intense X-rays and other radiation. This radiation comes from outside the event horizon and can escape, making accreting black holes among the brightest objects in the universe, even though the black hole itself emits nothing. As material in the accretion disk spirals closer to the event horizon, it accelerates to tremendous velocities, often reaching significant fractions of the speed of light. The innermost stable circular orbit, the closest distance where material can orbit without inevitably falling in, lies just outside the event horizon. Material at this radius whips around the black hole in fractions of a second, subjected to intense tidal forces and heated to extreme temperatures before making its final plunge across the event horizon. At the quantum level, something remarkable happens right at the event horizon. Stephen Hawking predicted that quantum effects near the event horizon would cause black holes to emit radiation, now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But at the event horizon, one particle of the pair can fall into the black hole, while the other escapes. To a distant observer, the black hole appears to be emitting radiation with a temperature inversely proportional to its mass. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so the effect is purely theoretical at present. But over unimaginably long timescales, Hawking radiation would cause black holes to slowly evaporate. The event horizon represents one of the most profound boundaries in physics, a one-way membrane in space-time itself. It's a place where our intuitions about time, space, and causality break down, where the fabric of reality becomes so warped that the normal rules no longer apply. Everything that crosses this boundary is lost to the outside universe forever, adding to the black hole's mass and slightly expanding its event horizon, while the information about what fell in appears to be lost forever, creating paradoxes that physicists still struggle to resolve. The edge of a black hole is truly an edge, not just of a physical object, but of our ability to observe, to know, and to understand the universe. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot, and water boils away. Too cold, and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone, because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star, where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions, the boundaries of the habitable zone depend entirely on the star's properties. Hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapor acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The Sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the Sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapor will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the Sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials. Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward might have compositions dominated by ices, rather than having the right balance of rock, metal, water, and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favorable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their stars' habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward. Another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams. When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or 1 billion Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into 2 beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust, composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos.